Hi, this is David Van Vranken here in Chemistry 51C at UC Irvine, and this is maybe the sixth lecture in the quarter. I wanted to start off by talking about a polymer. I went to put on one of my t-shirts, one of my favorite comfortable t-shirts, and I kind of pondered on why it seemed more comfortable than the others. And when I looked at the label, I noticed it wasn't just a cotton t-shirt. It had 5% spandex in there. And I thought that was sad that I didn't know the chemical structure of spandex or what that was in my shirt. I know what cotton is. And so I thought, let's talk about spandex. It's also known as lycra. The spandex is a polymer, and we haven't really talked much about polymers in our course so far. They do mention those in the book. Spandex, I think, is a commercial name developed by DuPont. It's an anagram of the word expands, so you kind of get the idea where the name spandex comes from. But in other places, like in Europe, it's known as elastane, also marketed as lycra. And the chemistry for making polymers for this type of polymer involves taking molecules that have two functional groups on each side. So for example, here's a reaction that I'm not sure we're going to show you this quarter, but it used to be in other textbooks, it's a standard reaction. And that's the reaction of alcohols adding to isocyanates. That really presages what's coming up in chapters 20, 21, 22, 23, 24, that we're going to be adding to carbonyl groups. And this weird functional group that you've never seen before, this isocyanate, has a really reactive carbonyl group. So alcohols or water, you would keep water out of this reaction, will easily add to the isocyanate. And if your alcohol has two OH groups on different ends of the molecule, and your isocyanate has two different isocyanate groups, then after one alcohol adds to an isocyanate to form a functional group called a carbamate that I don't think you've ever seen before. This is a carbamate. It's not an amide, it's not an ester, it's called a carbamate. And it can keep reacting on each side of the molecule to make these polymers that are thousands of subunits long. And that's the chemical structure of spandex. Here's a micrograph showing the strands of spandex under polarizing light, which creates those different colors. And so you wear spandex. Spandex is noted for its elasticity, its ability to stretch. And so you see it a lot in sports performance clothing, where maybe you as you move your arms or your body, you want things to be freely flexible and not feel bound up in any way. So that's spandex. That's lycra. So if you have any clothes, now you know a little bit more about the chemical structure of the clothing that you're wearing. Let's come back over and take a look at our lecture for today. This is the most important chapter in the book. And I mentioned just before we started that we have an exam coming up on Monday that covers electrophilic aromatic substitution and the acidity of OH compounds. But really, this chapter is it's a demarcation point between everything else you've learned in organic chemistry and the important stuff in organic chemistry, which is basically the rest of the quarter, really, for the most part. And so it's going to require a seismic shift in your thinking. So your tendency will be to think, it's natural to think that I can't learn anything new right now. I just have to get ready for Monday's exam. But you've got to absorb this material. This is super important. And if you get off on the wrong foot here and don't absorb this material and really embrace this idea that we're going to add nucleophiles to every carbonyl that we see, then you're going to be lost. So let's go ahead and talk about that. Carbonyls. My God, that's awesome. I'm so glad that we have finally hit the chapter on addition to carbonyl groups. So I want you to contrast two different types of potential reactive functional groups. I'm going to use ET here to represent an ethyl group. Just a little easier on the eyes, I think, than writing the molecular formula. And let's just imagine that I compare that with another type of electrophile that you may be familiar with. And that would be something where you can see an obvious leaving group there, like a bromide or a chloride or a tosylate. And what we're going to do, what you ought to be familiar with, is this idea that if you have nucleophiles, then in theory, you ought to be able to do SN2 type reactions and displace leaving groups. But that's really not how biology works. That's not how organic synthesis works. Why did they waste so much time trying to teach you about this idea that you can displace functional groups? As you know, when you get to secondary alkyl halides, this is not such a great reaction because you get competing E2 eliminations if you have a strong nucleophile, and then you end up in this sucky situation where you're trying to worry about, gee, is it E2 or SN2 or SN1 and SN? What a waste of brain cells that was, because that's not what we don't usually do SN2 type chemistry, because we don't want to worry about competing eliminations. In organic chemistry, what we do is we add to carbonyl groups. Let me come back and change my pen. Here's the way we normally form bonds in organic synthesis. This is the way biology forms bonds. Your biochemical systems work this way. You add to carbonyl groups, C double bond O, or if you're making nucleotides, you add to P double bond O. That's the way organic chemistry works. Let's go ahead and talk about contrast these two patterns of reactivity. So I want to try to encourage you to stop thinking in this fashion where everything you're looking for a leaving group and trying to do SN2 reactions. That's kind of old stuff. That's old thinking, and that thinking is not going to get you anywhere if you're stuck in that mode. What I want you to do first is I want you to think about the resonance structure for any carbonyl compound. There's a resonance structure that we can draw where we can take the electrons in the carbonyl group. So before I add to that carbonyl, let me just recognize the fact that there's a resonance structure where I bring the electrons up to the oxygen, and I draw the CO double bond instead as O minus and C plus. And when I draw it like this, I feel like it's a lot more obvious that carbonyl compounds are a lot like carbocations. So I'll just write here, wow, that's a lot like a carbocation. So you should already know that nucleophiles want to add the carbocations and so that carbocation can satisfy the octet rule. So if every time you see a carbonyl, you think of it as a carbocation, because of this resonance structure, it'll be easier for you to intuit that you should be attacking that carbonyl group. So that's what the rest of this quarter is going to be about, is this idea that we're going to add instead of doing SN2 every chance we get, we're going to do a process called addition. I'll just write addition here with a little abbreviation symbol there. So we're going to add to carbonyl groups, and there won't be a leaving group that detaches, but we are going to break a bond in these cases, and so we'll end up pushing the electrons up to the carbonyl oxygen, and we'll make a new nucleophile carbon bond. So this is the theme that we're going to be focusing on in chapter 20, 21, 22, 23, 24, and 25. Chapter 25 is on amines, but we'll still be adding to carbonyls in that chapter. So this is such a difficult transition to make. If it took you 9 months just to learn SN2 chemistry and SN1 chemistry, boy, we are going to have no time. So let's just, wow, add to carbonyls. Add to carbonyl groups to make bonds. Just cannot emphasize the importance of that enough. Okay, let's go ahead and take a closer look at a distinction between two classes of carbonyl compounds. So there's going to be some classes of carbonyl compounds where we have electronegative atoms attached. For example, we might have a chlorine here, or an oxygen atom here, OH or OR, or in some cases even an amide, although those aren't as good. And then in other cases, we'll have an H or an alkyl group, which can never act as leaving groups in any reactions we teach you in organic chemistry. Simple H or alkyl groups never act as leaving groups. So depending on whether we have chlorine, bromine, iodine, or or some oxygen substituent there versus H or alkyl, if we have something that's a potential leaving group, and it might not even be recognizable to you that that is a leaving group, and we'll teach you how to recognize those things. If there's a leaving group here, the overall reaction we're going to see is a reaction of substitution, and I'll walk you through the mechanism for that. So let's go ahead and take a closer look at what would happen here. If we have a potential leaving group here, the first step is always the same. That's addition to the carbonyl. If we take some other oh, look at this nucleophile that we learned way back in the alkyne chapter, chapter 11 in our textbook. Remember these acetylide anions, and they tried to tell you that you could do SN2 reactions? Nobody uses them for that. When people make acetylide anions in the laboratory, they use them to add to carbonyl groups. That's what we use them for in organic chemistry. That's how the first birth control pills, chemicals were synthesized. We still use those in the synthesis of pharmaceuticals. So don't forget your friend, the acetylide anion back from chapter 11 in the Gorzynski-Smith textbook. So you want to add to carbonyls, but let me go ahead and draw the intermediates that you get when we add in these two situations. One situation where there's a leaving group and the other situation where there's no leaving group. So if I add a methoxide anion to this carbonyl, let me go ahead and draw that methoxy group attached here. There's the chloride. I'm going to use that as a leaving group in a minute, just not yet. And then I have this oxide anion there. I'm going to draw one lone pair here because I know I'm going to need that lone pair in just a second. We would refer to this process as addition. So whenever you add to a carbonyl group and you don't have a leaving group leave, you kick the electrons up to the carbonyl group, and we refer to that mechanistic step as addition. And you would do the same thing over here with the down below when you add to just an aldehyde or a ketone where there's no leaving group on there. Oh my gosh, look at this carbon-carbon bond. Oh, that is so good. Oh my gosh, that feels great to make a carbon-carbon bond. Boy, we've waited 7 months in the organic chemistry series to make carbon-carbon bonds like that. And finally, that feels so good. Okay, when there's a leaving group, an acyl halide, acyl chloride, or an ester, or in some cases even an amide, we're going to push out this leaving group here. And so let me go ahead and use that O-. Look, I've got a nucleophile. You kind of learned that you can do SN2 reactions on alkyl chlorides, but if you have an O- or even a C-, we'll show you instances like that later, next door, it can easily push out this leaving group. So I just can't wait to use this lone pair that is right here. It's overlapping in space with the antibonding orbital. It's pushing, it's pushing, it's pushing. The O- is always there. It doesn't have to collide through an intermolecular process, and it can just so easily push out that chloride. So wow, that's amazing, really. So this is what we're going to see happening with esters and acid chlorides, and we refer to this process as an elimination step. Let me write it in red just for the sake of consistency. I'm not going to write the whole word. I'll just write elimination there. So this two-step process of addition and elimination results in substitution of the leaving group. It's not a one-step process. It is not a one-step SN2, but you can substitute leaving groups on carbonyls like chlorides and leaving groups that that aren't going to be comfortable to you yet. But notice how we've, in a two-step mechanism, we've achieved substitution of a substituent that was attached to a carbonyl. Big time theme coming up in chapter, I think that's going to be chapters 22. Let me change this. I think that's chapter 22 in the 5th edition of the Gorzynski-Smith textbook. Okay, when there's no leaving group on there, right? We have lone pairs over here on the on this oxygen down below when we add to an aldehyde or a ketone, but they can't push out any leaving group. There's nothing here that's recognizable as a leaving group. So that'll just sit there and sit there and sit there. You'd still refer to this first step as addition. But this is just going to sit there until we work up the reaction. There's a sodium ion in there that's just floating around, waiting to, nothing's going to happen with that. So that'll just sit there, and you can come back a day later and dump some water in there. And what will happen is when you dump some water in there, I'll write H2O, and I'm going to write the word workup. We're not adding the water to try to do SN2 reactions or anything fancy. We're just dumping some water in there, swamping it with water to try to protonate it. You just take a beaker full of water or dump some water in there, and you can protonate that O- And then you get a neutral molecule. And this is really the goal for organic chemistry, is to get neutral products that we can extract into organic solvents so that we can evaporate the organic solvents. I'm not going to draw the stereocenter. Of course, that's formed as a racemic mixture. We'll talk about that a little later. So there's two steps here when you do reactions of ketones and aldehydes, but it doesn't substitute the H or the phenyl on the original carbonyl. So just note here that this is a two-step process. It's step one is add, and then you have to remember to include the fact that you're doing an H2O workup when you add to an aldehyde or a ketone. Okay, let's go ahead and take a look a little bit further here at a class, the first class of nucleophiles that we're going to show you. So what's new about this chapter? We're teaching you to add to carbonyl groups, add nucleophiles to carbonyl groups. That's what organic chemistry is all about. That's what it is all about. I cannot say that enough. Okay, let's take a look at the first weird functional group that that I don't think you have seen before. You might have seen hydroborates if you covered oxymercuration reactions. I can't remember whether that was covered in the addition to alkenes section, but you didn't use it as a nucleophile. And here we're going to teach you how to use Hydrido 8 complexes as nucleophiles. Let me go ahead and show you those two Hydrido 8 complexes that you're going to learn about. One of these reagents, and I have to just think up for a moment here about how I'm going to depict this, has these long, I'm going to draw this freakishly long, these long nucleophilic bonds to aluminum. Now aluminum normally only wants 3 bonds, but they sell this reagent where it's got 4 bonds, so it's got a negative charge. And they sell this as the lithium complex. The sodium tetrahydroaluminate doesn't have good solubility, so it's not as common. So lithium, this is called lithium tetrahydroaluminate, would be the formal way to describe that. And the word aluminate, 8, tells you there's a negative charge on the aluminum. They also, another common reagent is sodium borohydride. And I'm going to draw these bonds normal sized. These are like typical second row atom type bonds. Boron's in the second row. This is tetrahydroborate, also called sodium borohydride, but I like the word hydridoborate because I like to focus on the fact that there's a negative charge. Borate tells me there's a negative charge on boron. Look, when there's a negative charge to aluminum, that means all the bonds to aluminum are nucleophilic. So, and it's not the aluminum that is going to form bonds. It's going to be the H's that form bonds. That H is going to want to attach to other things. That H is going to want to attack carbonyl groups. Now, these two compounds are not equally reactive. The one with the longer bonds, and this is generally true in organic chemistry, when you have longer bonds, you are more reactive. And if you have way longer bonds, then that means that this tetrahydroaluminate is way more reactive than the tetrahydroborate. So way more reactive. And these bonds, these H atoms, these hydrido groups, the H's are going to want to attack things. So let me go ahead and just draw this out here that we're trying to focus on these bonds here. Those bonds are nucleophilic. The bonds themselves are nucleophilic, and it's the H's that are going to be attacking things. Okay, so here's 2 reagents that you haven't seen used before as nucleophiles, and these are going to be total money for you. I promise you I'm going to have some version of this on my final exam. I don't know what problem I'll make up. If you go to any exam in any organic chemistry course, the final exam at the end of the year is going to have these reagents somewhere there in the exam. You just have to know how to use these in every single circumstance. And there's lots of ways to use these reagents. So let's get started on using tetrahydroborate reagents. So I want to start off by what you don't want to do. Let me start off with the more reactive one, which is tetrahydroaluminate. So I'll start over here kind of in the middle of the page where I draw this tetrahydroaluminate reagent. I'm not going to draw the bonds freakishly long here just to save space, but this is that tetrahydroaluminate reagent. And here's one thing you would never do. You would never put this reagent in water or in an alcohol. because you're just going to destroy the reagent. Because what will happen if you do that is these long nucleophilic bonds are also long and basic, and so they will instantaneously deprotonate the water or the alcohol, and they will do it so fast and so aggressively and so exothermically that as you generate hydrogen gas, notice it's the H that's forming the bond here. As you generate hydrogen gas, this thing is going to burst into flames. So I don't know how do I draw, can I draw a flame here? I don't know if I can draw flames. Flames, the hydrogen gas from the heat would catch on fire and catch, then if you had anything else flammable in there, you would end up with a fire. So we would never expose a super aggressive reagent like tetrahydroaluminate to either alcohols or to water, because it would destroy our tetrahydroaluminate reagent, and that's not what we use tetrahydroaluminates for. The idea here is that if you have a tetrahydroaluminate, and if you exclude, keep it away from, if you exclude things like water or OH groups, as long as you can exclude those, and you have a carbonyl within 1,000 miles, you're going to add to the carbonyl group. That's what we do with carbonyl groups. This is what tetrahydroaluminate reagents are super useful for. This is what you're going to be using them for this quarter, is you're going to be taking those sometimes I circle my charges if I'm worried you won't see them. We're going to be using these tetrahydroaluminate reagents to form bonds between the hydrido hydrogen and the carbonyl carbon. Remember, carbonyl carbons want to be attacked by stuff. That is what we're doing this quarter. And so you'll end up forming, if you start with a ketone, you'll end up forming an alcohol. Initially you'll form an alkoxide, but this is the idea. And it's easy to protonate an alkoxide, dump a bunch of water in there and you'll protonate it. So it's kind of the opposite of an oxidation. You learned how to use PCC and chromic acid to oxidize alcohols to carbonyls, and now we're showing you how to go back in the other direction. And again, there is a byproduct here. This species is called alane. It's kind of like methane, but aluminum only wants 3 bonds. So this tetrahydroaluminate is a super powerful and aggressive nucleophile, but that's not to say that you should be using it for SN2. It is not very good for SN2. Don't try to use lithium aluminum hydride, lithium tetrahydroaluminate for SN2 reactions. If you're doing that, you're thinking, you're kind of, it's not useful for those reactions. You have to use, to get that to work, you'd have to use some special conditions, solvent systems that we don't talk about in this quarter. So those tetrahydroaluminate is for reducing carbonyl groups. Now, let's go ahead and think in a little bit more about how we're going to use these reagents. And I'm going to have to teach you about enumeration of steps. And I don't think we've made a big deal about that yet. So let me go ahead and take a substrate, and I'm just going to pick one that looks kind of weird to you. Why? Just to try to get you to think outside the box. Okay, what do I see here? Yeah, there's a cyclobutane ring. Forget that, there's a carbonyl. Don't you want to add to that carbonyl? I sure do. But as soon as I see that carbonyl, I want to add a nucleophile right in there and make a bond. Okay, so if we wanted to convert this to an alcohol, then we use lithium aluminum hydride. Just go like this, it's easy, lithium aluminum hydride. But that will give us an alkoxide anion. And organic chemists don't want to work with insoluble salts like lithium alkoxides. What we want is neutral alcohols that we can extract into organic solvents and then evaporate the solvents, and we've got pure compound. So we have to follow this up, as I just indicated in that previous slide, is we have to follow this up with an aqueous workup. If we want to put a proton on that O- product, then we have to write that in here. And the book will often do it like this. I like to write the word workup there to make it absolutely clear. It's like, what am I doing with that water? I'm not trying to do SN2 or SN1 or use it as a nucleophile. I'm just swamping it with water to stick a proton on the O-, because nobody wants to isolate salts. You have to enumerate the steps. Step 1, you add lithium aluminum hydride. You go away for lunch. You come back after lunch as your reaction cools, warms back up from being in an ice bath. the flask being in an ice bath, then you come in and dump your water into the reaction. So these are two independent steps. And let me just make it absolutely clear here that if you write this out without enumerating the steps 1, 2, if you write it out like this and you don't put numerals of some kind there, then that's completely wrong. That is absolutely and completely wrong. I already told you what happens if you mix lithium aluminum hydride with water. The hydrogen gas catches on fire and you wouldn't get any of the carbonyl reduction. You would simply destroy your lithium aluminum hydride reagent. So this is totally wrong to write this out. So I'll just write totally wrong. That's wrong. You have to enumerate the reagents. Now, the book enumerates the reagents using these brackets, 1 and 2. And you'll find that I sometimes enumerate my reagents using Arabic numerals 1 and 2 with little parentheses there. I usually use small Roman numerals to indicate I'm not trying to isolate the products in between and purify them. It's just like when the reaction's done, you dump in the steps in Roman numeral 2. But if you used any of these types of enumeration systems, that's fine. Just to make it absolutely clear to anybody else that you're not dumping everything in there at the same time. If you don't enumerate it, then it indicates you're dumping everything in there at the same time. Now, I'm going to encourage you to do the same thing with sodium borohydride just because it's easier to remember. So let's go ahead and draw out with this idea here that if you can do the same thing, reduce ketones and aldehydes. And so let me just kind of highlight this here. You can reduce ketones and aldehydes and ketones with sodium borohydride or lithium aluminum hydride. So if we take, I'll do an aldehyde this time just to be different. So if we take an aldehyde and we treat that, we could do another 2-step process with sodium borohydride and follow that up with an aqueous workup. That's the worst looking 4. Let me see if I can correct that. There we go. I think that looks like a 4. And then we follow that up with an aqueous workup to protonate the O- that we generate. Again, you don't have to write the word workup, but because you're just now learning about these 2-step procedures with aqueous workups, I just want to make it clear we're not using the water for anything other than just to stick a proton on the O- so we can get a neutral alcohol product. Now, it just so happens that sodium borohydride, and you couldn't possibly have intuited this, sodium borohydride is so much less reactive than a lithium aluminum hydride. There's a special secret set of conditions that you can use when you use sodium borohydride. And that is this special instance. If you're reducing aldehydes and ketones, you can use sodium borohydride in methanol. I'll write it MEOH, or you could write it CH3OH. Without enumerating the reagents, it turns out that sodium borohydride decomposes, it reacts with the methanol so slowly that you can actually add to carbonyls faster than sodium borohydride deprotonates the methanol. So don't do that with lithium aluminum hydride. Only with sodium borohydride can you do this 1-step sodium borohydride and methanol procedure. But that's, I feel like it's easier for you to memorize if you always do this as two steps. So that would be, this would be okay if you did it in that way. All right. We need to talk about the fact that you end up forming a lot of stereogenic centers when you add to aldehydes or ketones. So let's talk about this. When you make a 4th bond, you have to think about, did I just put 4 different substituents on a carbon atom on an sp? Because if you did, you've generated a new stereogenic center that wasn't there before. So here's an example up above where if you do a sodium borohydride reduction of a ketone, then you'll end up forming a new bond here. And I didn't draw the H, but clearly there's a 4th bond here. And if you have 4 different substituents on that carbon, then that means you formed a stereogenic center. And unless I say otherwise, unless I say don't worry about stereochemistry, you need to indicate that there's 2 products to this reaction. There's the alcohol with hydroxy up, and then there's the mirror image with hydroxy down. If you're writing this out on paper and you write +E, every organic chemistry instructor knows that you mean the mirror image and you don't have to draw it. But really the correct way would be to draw the structure of the mirror image like this, and just draw that you also in equal amounts generate the product where the OH is going down. And in that case, the hydrido group added from the top face of that molecule. Those are mirror images. You would get both of those products in equal amounts. So let's go ahead and talk about what's going on here, right? If you have a ketone of any kind, where the substituents are not identical, and you add a nucleophile that makes a third different substituent, I'll go ahead and draw out the hydroborate species like this. And now let's go ahead and add that bond in. Boy, I just love drawing out this nucleophilic addition to carbonyls. Just feels so natural. That's what organic chemistry is all about, is the addition of nucleophiles to carbonyls. And it's a little bit weird for you because I know these hydridoborate and hydroaluminate reagents aren't really what you're used to seeing at this stage. So there's two different faces to this carbonyl. There's the bottom face and the top face. If the hydrido group adds in from the top face, I would need to indicate that. So let me go ahead and draw in that this hydrido group, I just want to change the way I'm indicating the stereochemistry here, that this hydrido group added in from the top face, and I'll make the ethyl group point backwards. I could have also made the phenyl group point backwards, but that's not what I had in my initial notes. So one product would result 50% of the molecules. Let's suppose you have 6.02 times 10 to the 23rd molecules in your flask. You know, half of those, the hydrido group is going to add from the top face, and the other half, the hydrido group is going to add from the bottom face. So let me go ahead and draw that in. Be a little more careful writing there. So the other half, that hydrido group would add in from the bottom face. And now I would draw the ethyl group pointing up. You know, there's multiple ways I could have drawn the enantiomers, as long as you're careful to check the S and R Conning-Gold Prelog assignments. You could have drawn these enantiomers in other ways. So now you've got a whole flask, right? You usually buy sodium borohydride, so there was a sodium cation in there. And so you'll have this whole flask full of sodium salts that you don't want. What you want to do is you want to make neutral molecules that you can extract into an organic solvent. And so you just swamp this with water. You dump a bunch of water in there. You know, if there's 1,000 times more water molecules than alkoxides, then you're just by equilibrium, you're going to protonate almost all the alkoxides. And so this is just a workup here. And so at the end of the day, what you would end up generating is a mixture of a racemic mixture of two different enantiomers when you generate a new stereogenic center. So always look when you add to carbonyls to make a fourth bond to see if you created a new stereogenic center. I'm just going to write plus E here, and I think I meant to make that into an H, so that's a neutral alcohol. So the product here would be racemic. Now, I wrote here that you may abbreviate enantiomers with E, with plus E, but that doesn't work on this sapling online homework system that we're using. So let me go ahead and take that out here just to be clear that you can't do this on sapling. You may abbreviate enantiomers with plus E. I'll just write, because this quarter we're taking our exams remotely using this online system, I'll just write not on sapling. So on the sapling system, if you want to indicate that there's an enantiomer, then you have to literally draw the mirror image or any other stereoisomer in order for the system to recognize that. So you can't say plus E. Okay, which means I have to be careful about how I ask those questions because I know it's time consuming to draw a second enantiomer, a mirror image of a molecule. There's a section in the book that talks about a type of reagent called a chiral reagent called the CBS reagent. I'm forgetting that it's Corey, but I forgot the name of the reagent. It's a borane compound with that's chiral, that can choose and selectively add to one phase of a carbonyl rather than the other. There is no reason in the world for you to memorize that reagent. So I would prefer you just skip it, but you know, you can read through it and it's interesting stuff for you to learn about, but there's no way I would ask you about that on the exam because I don't think it's important for you to memorize that particular reagent. But be on the qui vive, be on the lookout for formation of new stereogenic centers that weren't there before, because when that happens, you're going to generate a racemic mixture. You have no control over that. All right. Okay, I just finished talking about ketones and aldehydes. You add a hydrido group in, and it forms a tetrahedral center where the carbonyl used to be. But I want to introduce you to another reagent that doesn't really fit in here. It's not like lithium aluminum hydride. It's not like sodium borohydride. And you might say, oh, well, there's an aluminum in that reagent. And the reagent is called DIBAL-H, diisobutylaluminum hydride. These 4 carbon alkyl groups are isobutyl groups. There's 2 of them, so it's diisobutylaluminum with a hydrido group on there. And DIBAL-H, after this, you don't need to know the structure. I'm never going to ask you the structure. The book doesn't show you the mechanism, so I'm not going to show you the mechanism because it'll freak your mind out if I show you the mechanism. But when you treat an ester, not a ketone or an aldehyde, if you treat an ester with DIBAL-H, it replaces the ester alkoxide group with a hydrido group. And that is useful. Man, that's useful. Wow. Aldehydes are so much more useful than esters as far as organic synthesis goes. So this is really an important transformation when you do multi-step organic synthesis in the laboratory. So you need to know this 2-step procedure. You need an aqueous workup, just like we needed with lithium aluminum hydride. I'm not showing you the mechanism, but you need to know that any type of ester bond like this is going to be substituted. It's going to be substituted. That bond right there is going to cleave, and you're going to add the H group from the DIBAL-H. So it's super useful to turn esters into aldehydes. And it can be an ethyl ester, it can be a phenyl ester, it can be a long 50 carbon chain on there if you wanted, on the OR part of the ester. Doesn't matter. You're going to cleave that bond and make a new CH bond. And normally you throw the alcohol part away. That's usually discarded as trash, almost always. So usually it's ethyl or methyl, because ethanol and methanol are easily evaporated off. So I'll just write that this is usually the trash part, usually discarded. We usually just evaporate that off. Usually, so it's almost always methyl, but not always, usually discarded. I think we'll cover later in some of our problem sets cases where it's a cyclic ester and there's no way to discard it because it's the alcohol leaving group's attached. Let me go ahead and just draw an exotic example to try to kind of stretch our minds here a little bit. And we'll try to make this super fancy. So I'll put an alkenes here. I'll take a pyran ring. You don't know the name of that ring yet. I'll put a leaving group on the double bond, but of course you can't do SN2 or E or anything with that because it's on an sp2 centers. That's not going to react. But I'll just dangle off on here an ester. So CO2ET, an ethyl ester, would be a pretty common type of ester. And if I wanted to reduce this down to an aldehyde, so I could do some chemistry from chapter 21, for example, which you haven't seen yet, let's just suppose I wanted to change that to an aldehyde. Right, there's an H on that aldehyde. I just didn't draw it. Well, again, you use your DIBAL-H reagent, DIBAL-H. And then step 2, there's an aqueous workup, H2O workup. I can't resist writing the word workup because, again, you should be getting used to this idea of when you make alkoxide anions, working up those reactions by dumping in a bunch of water. And you can't just write DIBAL-H. And you cannot write DIBAL-H in water and not enumerate the steps. That's completely wrong. DIBAL-H would be destroyed by the water just like lithium aluminum hydride. So when I tell you to enumerate the steps, if you don't do that, that's wrong. So, right, if you have esters, this is a powerful reaction. I'm sure somewhere in this quarter we're going to have examples where we do multi-step synthesis, and one of the steps is reduction of an ester to an aldehyde using DIBAL-H. Remember that reagent. So not quite as common as lithium aluminum hydride or sodium borohydride, but still super common and super useful. Okay, let's go ahead and take a look at another reaction of esters that uses lithium aluminum hydride. So let me go ahead and draw out an uncommon, or maybe let me go ahead and try to draw out something that looks a little bit fancier than just a regular ester. So this ester has a ketone, or sorry, a double bond attached to it. So if we wanted to reduce this all the way to the alcohol, and you have to watch this pattern of reactivity here, then we use lithium aluminum hydride. And let me show you how this works. So we have to follow this up with an aqueous workup. And the product of this reaction still has this cis double bond on here. But it reduces the carbonyl group all the way down to an alcohol. And it cleaves this bond here. Let me go ahead and draw the bond that gets cleaved. And it cleaves this bond just like the DIBAL-H did. So you end up with, as a byproduct, this methanol as a byproduct in that process. So if it was an ethyl ester, you would end up with ethanol as a byproduct. And usually you do this with a methyl or ethyl ester because you're usually trying to evaporate away the methanol or ethanol. That's typical. So what am I not showing you here? What I'm not indicating that just happened is we added two equivalents. We added two hydrido groups to this. So lithium aluminum hydride actually carries 4 hydrido groups, and it can transfer all 4 of those in there. So actually, I'm not writing down stoichiometry here, but 1 equivalent of lithium aluminum hydride would be enough to reduce 1 mole of lithium aluminum hydride would be enough to transfer hydrido groups to 2 equivalents of the ester. And so I'm not worried about it in this particular case. You just have to assume that it's, when we're doing these reductions of esters with lithium aluminum hydride, that you're adjusting the stoichiometry. So the book shows you that you can take other types of even more reactive ester carboxylic acid type derivatives like acid chlorides and do this same type of reaction. So I can have an even better leaving group than a methanol or a methoxide leaving group and do this same process. Honestly, nobody would ever do this, but if you did, it would certainly work even better. We'll talk more when we get to chapter 22 about the reactivity of various different acid chlorides versus esters versus carboxylic acids. So you could do the same type of reduction here. And in this case, I'm not going to draw the chloride. We normally don't draw the lithium salts or the chloride salts as the product. We just show the organic products of the reaction. This is just, nobody would ever do this. It takes a lot of work to synthesize acid chlorides. If you go through the trouble of synthesizing an acid chloride, there's no way you're going to take it and reduce it right back down to an alcohol. It's just, this would not be in any way common. I can't envision ever asking you this because nobody would ever do this. It's not a useful process in synthesis, but the book seems to ask a lot about this, and you might get asked that question later on some sort of MCAT exam or graduate record exam to get to graduate school or something, but nobody would really do that. It's an academic exercise. Wow. So what's happening here is the hydridoaluminate is adding to the carbonyl group. We'll talk about this mechanism here. It's an important mechanism, and it'll help reinforce this idea that when you see a carbonyl, add nucleophiles to the carbonyl. Let's take an example of ester reduction. What's going on mechanistically when we add to an ester? We'll make this an ester of benzoic acid. Who cares what the R group is? Could be methyl or ethyl, those are typical. And when we add a hydridoaluminate reagent in there, lithium aluminum hydride, that long nucleophilic hydridoaluminate bond is going to add to the carbonyl. The hydrogen is going to form a bond to the carbon. So like this. Let me use my fancy red pen here. There we go. And so you form a bond to the carbon using that hydrogen atom, that nucleophilic hydrido group. Now, as soon as we do this, boy, this is going to freak you out. Oh my gosh, this is probably going to be the wildest thing you've ever seen. We're going to generate this intermediate where there's this nucleophilic O-, and right next door there's an alkoxide. And that alkoxide is going to act as a leaving group. Now, probably somewhere in the organic chemistry series, you were told, oh, alkoxides never act as leaving groups in SN2 reactions. Yeah, oh yeah, hydroxide never a leaving group in an SN2 reaction. That's SN2 reactions. Alkoxides are not leaving groups in SN2 reactions, and hydroxide is not a leaving group in SN2 reactions, but this is not an SN2 reaction. The nucleophile here, the O- lone pair, which is a strongly nucleophilic lone pair, is right next door to this carbon atom. See that carbon atom? This O minus is right next door and cannot ever get away. It's always pushing, always pushing. It has absolutely no problem pushing out the alkoxide anion as a leaving group. So when we talk about these intermediates that result from addition to esters or carboxylic acid derivatives, there is absolutely no problem pushing out an alkoxide anion. So if you thought you memorized that alkoxide couldn't act as a leaving group, that's only in SN2 that they were talking about. No problem. We're going to see this over and over and over again in this quarter, where alkoxide anions act as leaving groups, and hydroxide in some cases, depending on what the substrate is. So, so this might not be part of your normal repertoire of leaving groups that you're used to seeing. Now notice we've generated an aldehyde. And aldehydes react with tetrahydroaluminate. So, right, if you've got extra tetrahydroaluminate, or if we kept count here, there's actually more than one hydroaluminate bond on our starting material. I'm just going to draw this with, I'll just go ahead and draw this with another equivalent of the tetrahydroaluminate. But there's other species in there floating around that have these nucleophilic bonds. And right, this is the way I would encourage you to draw the mechanism, because who cares what the other three things are on this aluminum. There we go. So as soon as you generate that aldehyde, even faster than the original starting material, you can't stop this at this point. You can't stop it. The other molecules of tetrahydroaluminate, the second you generate an aldehyde, will react even faster with this aldehyde than they react with the ester. And so you'll end up adding a second time, and that generates this alkoxide product, where, let me draw the H that was there before, and now we've got two H's, and this is the product that results at the end of this reaction. It's just going to be sitting in there with your lithium salt floating around, Li+, right? If you had an Li+ counterion here associated with the lithium aluminum hydride. So that'll just sit there and sit there and sit there. You can come back 3 days later, but you need to come back if you want to isolate your product and work this up. Convert it to something neutral by dumping a bunch of water in there, so that now you can extract it into an organic solvent and then just evaporate the solvent, and you've created benzyl alcohol. So look what we've done. If you take an ester through two additions to the carbonyl group, get used to adding to carbonyl groups, we can convert esters to alcohols. Now, what happened to this OR minus group? Well, that's also there. It's usually ethanol or methanol. And so that usually just gets evaporated off along with any solvents that you use for the extraction. It would be rare that you would care about the OR group. Maybe if the OR group was some big heavy molecule that you couldn't evaporate off, you'd have to worry about that. So there's actually two products here. If I asked you to draw the products of the reaction, the products, I'd expect you to draw the methanol, but really we usually like to reduce esters with methyl or ethyl esters, because then we can just evaporate that part off. All right, I'm going to go ahead and stop right there. We've made some decent headway here. And when we come back on, I think, Friday, we're going to talk about reduction of amides. And the really key thing that we're going to get to, let me see how far off I am from that, is addition of carbon nucleophiles to carbonyl groups. And that's really the meat of this chapter, is forming carbon-carbon bonds. If you're an organic chemist like me, you love to form carbon-carbon bonds. Everybody who teaches in the organic chemistry series here at UC Irvine loves to form carbon-carbon bonds. So we're creeping towards really the pinnacle of the organic chemistry series, which is forming carbon-carbon bonds by adding powerful carbon nucleophiles to carbonyl groups.